Oxidation-reduction reactions. In an oxidation-reduction reaction, we have electrons that are being transferred from one reactant to the other. These are also called redox reactions because oxidation reduction is kind of a mouthful. So we have redox, reminds me of red box or a red ox, but there it is. I guess ox-red wasn't a good abbreviation. So redox, oxidation reduction. Many redox reactions involve something reacting with oxygen. And that's where the term oxidation originally came from, something reacting with oxygen. So here we have iron reacting with oxygen to form Fe2O3. So the iron here is an atom, has no charge, and over here the iron is now part of an ionic compound and it has a charge. And in order for an atom to become an ion, there has to be a transfer of electrons. Here we have the combustion of octane, and we're forming carbon dioxide and water. And so this also involves the transfer of electrons, although it is not at all obvious because all of these are molecular compounds or elements. But we have something reacting with oxygen. So that is also a combustion reaction. H2 plus O2 to form water. This is also a redox reaction. So a substance reacting with oxygen is going to be a redox reaction. This is an example of a combustion redox reaction, the reaction between hydrogen and oxygen to form water. Here we have a mixture of hydrogen and oxygen gases. It needs a spark to get it started, and then it goes kaboom, and fireball ensues. And what you get as a result is H2O, combustion redox reaction. Here's a redox reaction without combustion. This one does not involve oxygen. Here we have a metal reacting with a nonmetal. Metal element, nonmetal element. These react to form an ionic compound. Here we've got the sodium metal and chlorine gas, and these will react quite vigorously and form sodium chloride. There's an electron transfer involved because here we have sodium atoms and chlorine molecules, no charges involved. Here we have sodium ions. The sodium has lost an electron, and chloride ions, the chlorine has gained an electron. An electron has been transferred from one reactant to the other. So here we have sodium reacting with oxygen, sodium reacting with chlorine, a metal reacting with a nonmetal element. And if we look at these products, we see that they are ionic compounds that has sodium ions and oxide ions, sodium ions and chloride ions. It's down here as well. And when you look at this, you kind of get an idea for why we don't show charges in an ionic compound, because it gets really messy, right? But here we've got 4 sodium atoms becoming a total of 4 sodium ions, and the oxygen molecule becoming 2 oxide ions. Electrons are transferred from the sodium to the oxygen. Here, electrons are transferred from the sodium to the chlorine to make these ions. Any questions? Transfer of electrons. For an element to become an ion, it must gain or lose electrons. If one atom loses electrons, another atom has to accept them because the electrons have to go somewhere. There's no homeless shelter for unwanted electrons. They have to go from one thing directly to another. If one atom gains an electron, that electron has to come from somewhere. You can't go to the store and buy electrons. You have to get them from someone. So atoms that lose electrons are being oxidized. Atoms that gain electrons are being reduced. That's just how it's defined. So here we have the sodium atom going to a sodium ion, and it does that by losing an electron. The chlorine molecule gains 2 electrons to become 2 chloride ions. So here we have a loss of electrons, and here we have a gain of electrons. And so that's another one of those pairs of things that's hard to remember the correlation with, so oil rig can help. Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Oil rig. So it's fairly easy to see when ions are actually formed. There's a complete transfer of electrons. But you can also have a transfer of electrons that does not result in the formation of ions. It's not a complete transfer. You can just have a shift of electron density. So here we have a hydrogen molecule and a chlorine molecule. When these react to form hydrogen chloride, there is a shift, a partial transfer of electrons to the chlorine. The chlorine is more attractive to the electrons, and so the electrons are going to spend more time over here. So there's an increased electron density around the chlorine and a reduced electron density around the hydrogen. This is a partial positive charge and a partial negative charge. So the chlorine has gained electrons, reduction is gain of electron density, and the hydrogen has lost electron density, and so it's been reduced. Any questions? When we have nonmetals involved, like the hydrogen and the chlorine, it's harder to identify what's being oxidized and what's being reduced, especially when those molecules become larger than just diatomic elements. So we assign a number called an oxidation state or an oxidation number to each element to help track where the electrons are going before and after a chemical reaction. And so it's important to remember that oxidation states are not ion charges. What's confusing is that a lot of times the oxidation state for an ion is the same as the ionic charge. But you can have a molecule without any ions and you can still assign oxidation states to those elements. They are imaginary charges. So this is just sort of a trick, if you will, to help us figure out where the electrons are going, what's being oxidized, what's being reduced. Ion charges are real and measurable. Oxidation states are imaginary. So there's a set of rules for oxidation states, and as is often the case, it looks a lot more complicated when you write it all out. Once you see how it works, you're like, oh, well, yeah, we just do this and it's fine. It's like playing a game, right? You learn a new board game or a new card game, and at first it's really confusing and they're throwing all these rules at you and you're like, why am I even doing this, right? But once you get the hang of the game, you don't even need to think about it anymore. You just know how to play, right? Because it makes sense to you now. Same thing with oxidation states. So order of priority, we go through this list. So free elements, an element by itself like copper or chlorine, whether it's diatomic or monatomic, those have oxidation states of 0. If we have a monatomic ion, such as a calcium ion or a chloride ion, so this has an actual charge, the oxidation state is the same as the charge. So this would have a +2 and this would be a -1 oxidation state. Number 3 here, this is the same idea as with ionic charges. The sum of the oxidation states in a neutral compound is 0. In an ion, it equals the charge on the ion. So for H2O, the hydrogen and the oxygen may have non-zero oxidation states, but because this is a neutral molecule, the charges add up to 0. The oxidation states, sorry. Here, NO3 minus, overall this has a -1 charge, so the oxidation states have to add up to -1. In compounds, metals will always have positive oxidation states, and those oxidation states are the same as their ion charges. So that's convenient, but it can also be confusing. And then the nonmetals. This is where we really need the oxidation states. The nonmetals have oxidation states assigned according to this list of priorities. So this is a list in order. So fluorine gets to be -1 first. The way I think of this is it's an order of who's in line to get what they want. And what fluorine wants is to have an oxidation state that is the same as the charge it would have if it was an ion. So it would like to be -1. If fluorine is present, fluorine gets what he wants, she wants. Hydrogen is next. Hydrogen would like to be +1 because hydrogen would have a +1 charge as an ion, right? What charge does an oxygen ion have? -2. Well, oxygen is third in line. And then the group 7A elements, they all take -1 charges. Group 6A -2, group 5A -3. So the oxidation states that these things have are the same as the charges they would have if they were an ion. But not everybody can have what they want all the time. And so there's a list here, and we need to remember this list. And you might like, wow, you're asking us to remember an awful lot of stuff. Well, I've got a trick for you here. You know what Ph is? Oh, I spelled it wrong. That's really bad. Okay. Wait a minute. Ph. 765. Okay, it's supposed to be a P. What's Ph? Noodles. Noodle soup. Yummy, yummy noodle soup, right? So Ph. Remember that. And the PH makes the F sound, so this is okay. So FHO and then 765. There's actually a restaurant, Ph 76. It's like oxidation states. Ph 76. So fluorine, hydrogen, oxygen, 765. It's possible to have fractional oxidation states, so if that shows up sometime, don't freak out, it's okay, because these are imaginary, right? You couldn't have a fractional charge on an ion because that would mean you've gained or lost part of an electron. Not possible. But fractional oxidation states, because they're imaginary, are possible. And just so you don't get confused by what I'm doing, the sign is written before the number for oxidation states, after the number for ionic charges. I'm not going to hold you to that, but I follow that most of the time, and so I'm not just being random, I'm actually doing it for a reason. Okay, so let's do some examples here. Assign an oxidation state to each atom in each element, ion, or compound. So for A, we have, this is an element, right? Chromium, does it have a charge on it? No. So what's its oxidation state? 0. How about the chromium-3 ion? It has a +3 oxidation state, same as its charge. Here we have carbon tetrachloride, a carbon and 4 chlorines. Is this an ionic compound? No, it isn't. It's 2 nonmetals. So there's no ion charges to go by, so that's when we pull out Ph 765. So the chlorine and the carbon are going to each have an oxidation state. all the chlorines, there's 4 of them, they're all going to have the same oxidation state as each other, because how would you decide that this one gets one and the other gets something else? That's just not going to work out. So Fa765, do we have any fluorines? Nope. Hydrogens? Nope. Oxygens? Nope. Group 7 elements? Yeah. Chloride's group 7. So chlorine gets to pick what it would like. What would it like? -1. Each one will be -1, right? Just like ions, except it's not an ion. So the chlorines are each -1, and there's 1 carbon. All of the oxidation states have to add up to 0 for this neutral molecule. So what does carbon have to be? +4. So it's just like ions. Here I've got carbon and I've got 4 chlorines. And they each have a -1 oxidation state. That's a total of -4. And so this +4 oxidation state must be divided just 1. So that's just like ions, even though it isn't ions. SRBr2. So this is a compound. Is it an ionic compound?
Yes.
Yeah, it is. So strontium ion. In this compound, strontium actually has a charge.
That's 2.
Yeah. Its charge is 2+, its oxidation state is +2. What's the charge on the bromide ions in that compound?
-1.
Yeah, -1. So each of the bromides has a -1 charge. Each of them has a -1 oxidation state. The strontium has a 2+ charge. It has a +2 oxidation state. So when you have ionic charges, the oxidation states are the same.
But then when it's molecular, that's when you use the Fa765.
Yes. When you don't have any ions, that's when you need the Fa765. So SO3.
What's the negative charge?
Yeah, so oxygen gets to pick, because FHO, oxygen comes first in the list, oxygen wants to be -2. And then sulfur has to be whatever is necessary so that all the oxidation states add up to the overall charge, which is 0. What's the sulfur have to be here? +6. So there's 3 oxygens. They're each -2 and 1 sulfur, so it has to be +6. Here we have a polyatomic ion. There's 2 nonmetals in this, a total of 4 atoms in this ion. We know that the overall charge is -1, but we're still going to use Fa765 to get started on this. So there's nitrogen and there's oxygen. Fluorine? Nope. Hydrogen? Nope. Oxygen. Oxygen chooses -2. That's what it would like. So what does the nitrogen have to be? +5. So this is a little trickier, and so, draw a picture if you need to. This one's -2 and -2 and -2. So that's a total of -6. And I need these to add up to -1, right? Because that's the charge on the ion. So this needs to be +5. Any questions? So identifying redox reactions. We talked about oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. We can also talk about that in terms of the oxidation state. Oxidation is an increase in the oxidation state. How does the oxidation state increase? Become more positive by losing electrons. So increasing oxidation state and loss of electrons are the same thing. Reduction is a decrease or a reduction in the oxidation state. Oxidation state goes down, becomes less positive, more negative. That happens by gaining electrons. So if we look at the reaction between carbon and sulfur to form carbon disulfide, we have two nonmetals reacting. Here, this carbon has a 0 formal charge, oxidation state, and the sulfur has a 0 oxidation state. Over here in the compound, we think of Fe765. There's no fluorine, no hydrogen, no oxygen, no group 7, but sulfur is in group 6. So sulfur gets what it wants. So it wants -2. And then this is a neutral compound, and so the carbon must be +4. Then we can see that the oxygen went from 0 to +4. It went up in oxidation number. That's oxidation. The sulfur went from 0 to -2. That's going down. That's a reduction. Any questions? Use oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. So we're going to assign oxidation numbers to all of the elements. Each element has an oxidation number. So here we have tin. What is it? 0. It's an element by itself. The first place to look when assigning oxidation states is there an ion with a charge? Then we're going to use that as the oxidation state. So here we have HNO3. There's 3 nonmetals, right? So now we're going to use Fe765. Fluorine, nope. Hydrogen, there's a hydrogen. So hydrogen picks +1. And now nitrogen and oxygen are fighting it out, but oxygen's next on the list. What does oxygen always pick? -2. And then nitrogen is low guy on the totem pole. He has to be whatever is necessary. So again, this one can be a little messy to think about. So I have hydrogen and nitrogen, and I have 3 oxygens. Each of the oxygens is -2. The hydrogen is +1. We don't know what the nitrogen is. So a total of -6. That's our question mark. And this is +1. And what do these need to add up to? 0. This is a neutral molecule. So the question mark here then has to be 5. So +5. SNO2, is that an ionic compound or a molecular compound? It's ionic. There's actual charges here. The charges of the ions are their oxidation states. What's the charge on the oxide ion? -2. Each of them is -2, right? And so then the tin has to be +4. Here we have NO2, molecular compound. Who gets to choose first, nitrogen or oxygen? Oxygen. Fe765, oxygen comes before group 5. So the oxygen's going to choose -2. What does the nitrogen have to be? +4. Now, this coefficient of 4 in front has nothing to do with it. That just says there's 4 of these molecules. In each of these molecules, we have 2 oxygens, each with a -2 oxidation state, 1 nitrogen with a +4 oxidation state. Water. Two nonmetals, Fe765. What does hydrogen pick? +1. And then what does oxygen have to be? -2. which happens to be what oxygen would like anyway. So I think of hydrogen and oxygen here being pretty happy with themselves, right? And it turns out that water is a very stable compound. Okay, so now that we did all of that, we're looking for the element that's oxidized and the element that is reduced. So we're not going to say that HNO3 is oxidized or reduced. We're going to talk about just a single element. So we're going to go in here and see who has changed their oxidation state. So tin, just start with that one because it's first. Tin went from 0 to +4. That's a change? Was that going up in oxidation state or being reduced?
Just gaining electrons.
It's actually losing electrons.
Oh, the charge is going up.
Yeah, charge is going up. It's confusing because losing negatives is gaining positive. Right? So this is oxidation. I really like the reduction is the reduction of the oxidation state going down. Okay, so hydrogen. Here's hydrogen is +1 and here's hydrogen +1. Nothing happened. The nitrogen went from +5 to +4. That's different. Is that going up or down? Yeah, that one's reduced. And oxygen is -2. Over here, oxygen's -2, -2, -2. It just stayed the same. It just got split up and spread around with other people. Any questions? If something is oxidized, it's losing electrons. There has to be something that's reduced to gain those electrons. It's possible to have multiple things being oxidized and or multiple things being reduced, but that doesn't happen very often in Chem 1A. So oxidation and reduction must occur simultaneously. If an atom loses electrons, another atom must take them. Okay. So before we add the agents, any questions about oxidation and reduction? So let's talk about movie stars and their agents, right? So what does the agent of a movie star do? Do they star in movies? The agent doesn't star in movies. The agent arranges for the movie star to be in movies, right? So the agent arranges for something else to do something. The reducing agent is the reactant that causes another element to be oxidized. So the reactant that reduces, I'm sorry, I said that wrong. That was really, really bad. I wish I could rewind it. Start over again. The reducing agent doesn't get reduced. It causes something else to be reduced. Just like the movie's agent doesn't star in the movie. The reducing agent causes something else to be reduced. In order to cause something else to be reduced, you have to be oxidized. The oxidizing agent causes something else to be oxidized. The oxidizing agent gets reduced. That's not confusing at all. Sorry, I didn't make this stuff up. Determine whether or not each reaction is a redox reaction, and if it's a redox reaction, identify the agents. So there's a couple of ways we can go about identifying redox reactions. We can assign oxidation states and see if they are changing. That always works. We could also just kind of look at it and think about it. Here I have two elements. What are their charges?
+1 and -1.
Well, those are the charges they will have when they become ions, but over here, does lithium have a charge? It's 0, and the chlorine is 0. And here they get charges, right? So electrons are being transferred. This is an oxidation-reduction reaction. So this is a redox. Let's just identify them first, and then we'll go back. Here, this one is a net ionic equation. We have good old Al here. Aluminum becomes aluminum 3+. Does that involve electrons moving around? Yep. And here we have tin with a charge going to tin without a charge. Also a redox reaction. Here we've got a lot of switching around going on. We have lead and nitrate, lithium and chloride, and then they're swapping partners. Let's think about how we do that. This is lead 2 and nitrate, and this is lithium ion and chloride ion. And then over here, we've just swapped partners. We just switched partners. We didn't actually change what the ions were. This is still lead 2. It was lead 2 over here. Is that a change in oxidation state? No. Here's nitrate and nitrate. Did anything change electrically? Nope. Lithium plus, lithium plus. Same. Chloride minus, same. Were any electrons transferred? No. This is not a redox reaction. You can go through and assign all the oxidation numbers. But I feel like if there's charges, it's easier to just look at the charges first. Here we have carbon and oxygen. And this forms a molecular compound. This is where oxidation states are going to be more helpful. You could also remember that combustion reactions are redox reactions. But what's the oxidation number for carbon? And for O2? 0. And in this compound, who gets their choice? Oxygen. So oxygen chooses -2, and carbon has to be +4. So carbon changed and oxygen changed. Is that a redox reaction? Yeah, it is. So any questions about identifying the redox reaction? Now it asks us to identify the agents, the oxidizing agent, the reducing agent. Since we were just talking about this one, let's start at the bottom and go up. The carbon is going from 0 to +4. Is the carbon being oxidized or reduced? Oxidized. I'm just going to call that ox. And the oxygen is going from 0 to -2. Its oxidation number is going down. It's being reduced. So the carbon is being oxidized, but the carbon is causing the oxygen to be reduced. So carbon is the reducing agent. And oxygen is the oxidizing agent.
So the carbon and the oxygen don't have charges like that.
Right.
But they would in a regular reaction.
No. This is a molecular compound, so it's covalent bonds. There's no ions involved. So our oxidation states are kind of like pretending if it was ions, what might they be? Let's, fairyland. There are no actual charges. We're making up imaginary charges. And it's based on things like electronegativity and all kinds of other factors that get a little bit complicated. And so doing the oxidation numbers actually is a simpler way of identifying what's being oxidized and reduced, believe it or not. So the carbon is being oxidized, which means that carbon is the reducing agent. The oxygen is being reduced. The oxygen is the oxidizing agent. They're like, backwards. Okay, let's look up here. Lithium and chlorine reacting to form lithium chloride. So this lithium here, what's its oxidation state? It's the same as its charge. 0. And the chlorine? 0. This is an ionic compound. What's the charge on the lithium ion? Positive 1. And so its oxidation state is +1. And chloride ion has a -1 charge, has a -1 oxidation state. Lithium goes from 0 to +1. That's going up in oxidation number. So lithium is being oxidized, and chlorine is going from 0 to -1. That's going down, reduction. Oops, there's no oxygen there. So if lithium is being oxidized, what kind of an agent is it? It's a reducing agent. The chlorine is being reduced, it's the oxidizing agent. Okay, number 2 is actually the easiest one. Here we've got aluminum with no charge going to aluminum with a +3 charge. If we want, we can think of this in terms of losing and gaining electrons, or we can think of going up and down in oxidation state. Let's think of it as electrons. How does aluminum become a +3 ion? Does it gain electrons or lose electrons? Loses electrons, right? Oil, rig. Oxidation is loss of electrons. So the aluminum is being oxidized. The tin is going from +2 to 0. It does that by gaining electrons, so it's being reduced. We're identifying the agents. So aluminum is being oxidized. It's causing the other thing to be reduced. So it's the reducing agent. And SN, that's a 2+, is the oxidizing agent. Any questions? The oxidation numbers and identifying what's being oxidized and reduced is much more important than getting the agents straight. So if you're struggling with this whole concept, I give you permission to just blow off the agents. At most you'll lose and miss one question on an exam, maybe one question on the final, that's it.
That's the easy part.
That's the easy part. Well, good. So, activity series. If we put a strip of magnesium metal into a solution of copper ions, a chemical reaction will occur. The magnesium goes from the element magnesium to magnesium ions. So it's being oxidized, and the copper ions go to copper metal being reduced. And so we see copper being deposited on the surface of the magnesium, and we see the color of the solution fading. Right? The color is from the copper ions. Copper ions are becoming copper atoms, and the magnesium is going into solution, but the magnesium ions don't have a color. So this happens because magnesium has a greater tendency to lose electrons than copper does. The reverse reaction, stick a piece of copper in a solution of magnesium ions. You can wait as long as you want, nothing will happen. The reaction does not go the other way. Copper doesn't lose electrons to magnesium. So the activity series for metals helps us to predict which reactions will occur and which ones will not. You can kind of think of it this way, that copper is going to grab those electrons. Copper wants the electrons. Magnesium's like, yeah, whatever, you can have them. Just doesn't care as much. So in this activity series, we list the metals in order of decreasing tendency to lose electrons. So the top ones have the highest tendency to lose electrons, and the ones at the bottom are the lowest. We write each of these as an oxidation half reaction, just showing it losing electrons. If you write that in the reverse, it's an oxidation reaction. I'm sorry, it's a reduction half reaction. And if you put two half reactions together, they make a single complete reaction. So this is the activity series. And good news, you don't need to memorize this. If you need it on an exam, I'll give it to you. So lithium, these are all written as the loss of electrons, right? So oxidation is going from a zero charge to a plus charge, a zero oxidation state to a plus oxidation state. So lithium loses electrons the easiest in this list, and gold loses electrons, it's the most difficult. So anything at the top of the list will, when paired with the reverse of something below it, will give us a spontaneous reaction. Can't remember what's on the next slide. So let's look at that copper and magnesium. We had magnesium and copper ions, and a reaction occurred where we got magnesium ions and solid copper metal. So we can write this as two half reactions. The magnesium, when it goes to magnesium ion, is giving up 2 electrons. The copper ion, to become the element, has to gain 2 electrons. If I add these two equations together, I get this one. Everybody okay with that? The electrons don't show up in this equation because they're transferred directly from one thing to another. But we can pull it apart and look at what's actually happening. The magnesium is losing 2 electrons. The copper ions are gaining 2 electrons. So when we talked about like precipitation reactions, we looked at the ions going to a party with a partner, right? Here, could we have just copper ions? No, there has to be some other ion there. We can have magnesium atoms, but we can't just separate charges. Nature really doesn't like that.
Since copper has a +2, would it still be 0 for the oxidation? Or would it be
Its oxidation state over here is 0, and here it's +2. So what might actually be going on here is we might have magnesium and maybe copper 2 chloride. right? So here, copper is an ion. It's got to come with an anion. So I told you I think of this as the guy and this is the girl. And what about magnesium? Magnesium's a metal, but he's not with anybody, so he's going alone, right? Is he really happy about that? Probably not. Here, copper is got a charge because he's got a date, right? So copper's got a date. He's taking a girl to the party. He's like, yeah, this is good, right? So then at the party, what happens? Well, this is an activity series. You could also think of this as maybe a list that some of the high school girls are keeping of who's the hottest guy in their class, right? You could imagine that happening. Well, lithium is the hottest, right? So as we go down here we have magnesium, and copper's way down here. So magnesium is more attractive to the girls. The girls like him better than copper. So here we've got copper, who's kind of a dork, but he got a date to go to this party, and here's magnesium, and he's a stud. What's going to happen at this party? Magnesium's going to take the girl. Magnesium's got the chloride now. And what happens to copper? Poor guy goes home by himself. You can imagine that, right? I mean, this is weird, dorky, stupid, whatever.
Does he still have a charge?
No, he doesn't have a charge. He lost his charge. His spark is gone. He's like, ugh. So magnesium came in alone. Copper came in with the girl. When we look at this reaction, we don't see the girl, because it actually doesn't matter who the girl is. They're just, I mean, these guys are chauvinist pigs or something, I don't know. They don't care who they are with, they just need to be with a girl, right? It gets very ridiculous very quickly. But you remember, so copper has a charge, that means he's got a date, right? And then after this all mixes together, magnesium's got the charge because he's got the girl, and copper's off by himself.
Why does this actually make sense though? I'm like, oh, okay.
Right? It makes sense because I've spent decades explaining this to students, and this one seems to work.
So if they have a charge, they're part of a compound.
Yes.
Even if it doesn't show the other
Yes,
element.
exactly. So when we look at an equation like this, that's a net ionic equation. What's happened here is that chloride is a spectator. Does chloride actually get changed? No, she just goes home with somebody else. But magnesium and copper, something happens to them, right? Copper lost his relationship status, and magnesium gained relationship status. Facebook official. So we can look at this list, and whichever metal is higher on the list is going to have a charge at the end of the reaction. It's going to have the girl. Okay? Any questions? Anything I can clear up? Long time ago, there was a Saturday Night Live skit. ¿Quién es muy más macho? And so I think of this as the más macho list. Lithium is the most macho. Okay. Which metal is most easily oxidized? So first, let's think about this. What does it mean to be oxidized? To lose electrons. So these are going to get charges, positive charges, right? Positive feelings. So they're going to get into a relationship, right? So who is the most easily oxidized? Well, we have to look at the list that the girls made, right? Who's most desirable? Sodium, chromium, or gold? So here we go on the list. There's sodium, there's chromium, and gold's way down there. I know. Gold is just dense. He's shiny, but he's really dense. So we see that sodium is the most easily oxidized. So if we put sodium with chromium ions, a reaction would occur. If we put sodium ions with chromium atoms, nothing's going to happen. Because a sodium ion has the charge, he's got the girl, he's not giving it up. He doesn't have to. Predicting spontaneous redox reactions. Determine whether each redox reaction is spontaneous. Is it going to happen in the direction that it's written? So what do we have going on here? Here we've got zinc. Does zinc have a charge? No. He doesn't have a date. Going alone. Here's nickel. Nickel has a positive charge. Does nickel have a date? Mm-hmm. Afterwards, zinc's got the girl, and nickel goes home by himself. So we predict whether this is going to happen or not by looking at who is cooler, zinc or nickel. And we have to go look at the list for that. So we're looking for zinc and nickel. There's zinc, nickel. So zinc's going to get the girl. So here's zinc with a charge. Come on, iPad. Here's zinc with a charge. Zinc got the girl. So is this going to happen? Yes. So this is spontaneous. Zinc and calcium. Well, we have to go look at the list again. Who's more attractive to the ladies? Calcium is. Calcium is above, right? So then when we look at this, here we have calcium. He's more desirable. He's got the girl. He's got this positive charge, positive vibe. I'm like, yeah, I'm up, right? Good days. And here's zinc. Because calcium is more desirable, more easily oxidized, zinc is not going to be able to take the girl from him. So we can write a chemical reaction for this, but it's not going to happen. This is non-spontaneous.
So it's non-spontaneous. That means it can't happen at all.
That means it will not happen on its own. You can force it to happen, but you have to put energy, you have to put money into it. You basically have to pay the girl to go home with the other guy. That's the only way you can make it happen, right? I know, it just blossoms and grows, right? It's this extensive alternate reality I've got going on in my head. It's really kind of a crazy place.